Okay, this week we have Ruihan from Cornell, and she's going to be telling us about differentially private data release for linear regression.
Yes. Hi. Hello, everyone. Yeah, I'm Ruihan. I'm currently a fifth-year PhD from Cornell University, and it's great for me to give this presentation. So I will introduce our recent UAI paper, Differentially Private Multi-Party Data Release for Linear Regression. This is the joint work with Xing, Yuanshun, Jiankai, Tianyi, Kilin, and Chong. Okay. Let's first talk about how the data is distributed. In the example at this page, each user has a set of image label pairs. For example, the first users have dog, cat, bird with their labels, and the second user has cat, fish, dog with their labels. In this example, each user has the complete single data, but they have different pairs of data. In the form of the data matrix, different users have the different rows of this data matrix, or say the data is horizontally partitioned. But the vertical distributed data is a bit different. Look at these three hospitals. The data have the same set of patients. Say here, Alice, Bob, Charlie, and so on. But due to their different functionalities or the responsibilities, they hold the different attributes. So the first hospital, because they have the special blood test instrument, so they have they are responsible to collect all the blood test results for the patients. And the second hospital, it may has the most experienced doctors with the most advanced instrument for the liver. So people will go there to make the diagnosis to see if they have liver cancer or not. So this hospital has the most information of liver cancer, and the third hospital they may be responsible for the physical examination, so they collect all these results for the patients. Okay, so then in this data matrix, right? Each party, they have all individuals, but they hold different attributes, which are the columns here, and here the data is vertical partition. So different hospitals have their own database. So the first hospital have 2 attributes, second has 2, third has 1. And they want to have a global data with all these attributes. Because with the global data, researcher can explore the data, study whatever the relationship between any 2 attributes or 3 attributes, can study the relationship between them, and that might be helpful for the real-world application. Okay, so initially parties have aligned a data points. So so the aligned means that the first rows we know that they are from Alice, and the second they are from Bob, and so on. but they have different attributes of them. Then the data release algorithm will take control of the first local computation, how they process their own data, and second, the communications between the parties. Then it will output a new data set with k data points. So this new data set, the number of data we don't require that k should be the same as the original data sets n. But we hope that it will keep all attributes. So here it keeps all 5 different attributes of all those parties. Okay, so now we are talking about the goal of the release data. Yes.
Yeah, sorry, I have a quick question. Are you assuming that all these data sets have the same number of users, or is that not a necessary assumption?
Yes, we assume that they have same number of data because those data is assumed to be aligned.
So you're assuming that they've already done some intersection and figured out the common users across them?
Yes. So yes, in this paper, we assume data has this properties, and I know that some recent work is studying how to privately find such intersections and so on.
All right, thank you.
Yes, thanks for the questions. Okay, we can continue. Yeah. So for the goal of release data, the size of the release data might be different. It could be fewer than the origin, but the attributes should all be kept since we know the semantic meaning of those attributes, and we want to study the relations between those variables. So this is the detailed utility goal that we want to achieve. As a data release algorithm, we consider the linear regression task with arbitrarily selected features and labels. So features and label are selected from the attribute sets in the release data. For example, here we choose red and green as the selected features, and choose the blue one or purple one for the label. And we want to study the linear regression task between them. Yeah, so for arbitrarily selected features and label, we hope that the linear regression model learned from release data would perform well with respect to the objective here. So the loss here is the expectation of your squared error, and the randomness. The data here is sampled from the private data distributions. So we assume that in the private data set, each row are sampled independently from the same distribution. And this problem has its closed form optimal solution, which is the inverse of XX transpose the expectation of it, multiply the this expected vector. If we assume that this matrix is positive definite, Then specifically, we expect that this linear model, because we already know the closed form of the optimal solution, we hope that the linear regression model learned from released data would be close to this optimal solution when the size of private data sets is large enough. And we define the closed in this form, in this asymptotic convergence format. So we expect that this learned model, WN learning, is close to W star as much as possible. So the randomness here in this P may come from the data sampling process and the algorithm we design. Okay, so we just talked about the utility goal of the release data. Now we discuss the privacy protection as a data release algorithm. I'm going to introduce a simple framework of the data release algorithm. So initially, each data has their own data matrix, D1, D2, and D3. Then the first step is to generate a random variables B and share it among different parties, as shown in this figure. So this B, we can say that it could be a collection of random variables. It doesn't have to be single values. We just use a unified notation here. And second step, we have this local privatization algorithm, a private. So this a private takes the private data matrix DJ and the random variable generated in the first step as input, and it will output a new data matrix for the party J. So you see these private algorithms outputs, each party, they output their own new data matrices. And then they can jointly release the data by concatenating these new data matrices. So it is of course possible that some more complicated algorithm parties can have more communications before the learning, before the algorithm, inside the process and after the process. And but this simple framework data release of data release parties only have one communication, that is sharing the random variable. And this is what our the framework that our paper focuses on. Yes, so just let a comment here that it could be more complicated, but probably need more complicated privacy definition for the algorithm. Okay, then I will define what kind of algorithm keeps the data private. We utilize the differential privacy as a tool to protect the data. In the previous framework, we have the local privatization algorithm, and we require that it should be differentially private. So I will briefly introduce what is the differential privacy here. So consider two data sets, D and D prime. They are different at exact one data point. Here, the ith data point highlighted by the red. And if a randomized algorithm A is differentially private, then the output of this algorithm from D and D prime should be mostly the same in the distribution level. So the distribution of these two randomized output should be close enough. With this property, people are hard to infer any single data's information from this randomized output. And this is the rigorous definition of differential privacy. So we see that the epsilon and delta, these two parameters, control the level of similar. When epsilon and delta are 0, these two distributions are exactly the same, and smaller epsilon and delta is stronger guarantee. Okay. Then back to our case, we further need this DP algorithm. The probability inequality here is conditioned on the shared random variable B. The reason is that the B is shared among parties, and each party want to protect their own data privacy against not only the public, but also other parties. And other parties, all parties, they all know this B. So we want that this B won't contribute the DP algorithm. But this B might be helpful for the utility, and we will see it later.
Sorry, quick question here. Do you assume
Yes.
that in each data set, every user has only one training example, or a user can have multiple training examples, say for every hospital? Just wondering if this is like example level DP or user level DP, the notion that you're using.
Okay, yes, so this is example level DP. So there's no user concept here.
Okay, thanks.
Yes. Okay. Then to summarize the problem setting, the first, the data is vertically distributed. Different parties have their columns in this data matrix. And secondly, for any selected features and label, learner can learn a good linear regression model from the release data. And we hope that this learned model converges to the optimal solution in probability. And thirdly, the local data privatization algorithm, a private, should be epsilon delta DP, condition on the random variable that is shared among all parties. So that's for the problem setting. Do you have any questions? Or I'll move on. Okay. Okay. So then we talk about the method, how to release the data. So the first try is to directly apply the Gaussian mechanism. So the Gaussian mechanism is that we can add the additive noise, Gaussian distribution noise to a function to make the probability density functions are closed, and larger variance of this Gaussian noise will make this two distribution more closed. And so the here is the formal definition of Gaussian mechanism. That is for any deterministic or real valued function f with the sensitivity as f. So the sensitivity is defined as the maximum difference between the output of a function for any neighboring data set D and D prime. We can define a randomized function by adding Gaussian noise to this f. So R is sampled from Gaussian distribution, multivariate normal distribution with this designed variance. If this sigma is large enough, then this post function of f is guaranteed to be epsilon delta dp, and we denote this epsilon delta related value for the sigma as sigma epsilon delta for the notation simplicity later. Then we'll see how to apply the Gaussian mechanism in this data release task. The difference between them is the difference between the two data points by neighboring definition. And then if we have the assumption that each entry is bounded by 1 for all those data matrices, then the sensitivity of function f, so function f here is the identity function. Then we can compute that it's smaller than 2 square root of dj, which is further smaller than 2 times the square root of dmax. So the dmax here is defined as the maximum dimensionality of attributes among all parties. We can then define the local privatization algorithm here, which is simply adding the noise on top of the private data matrices with this variance. Okay, and according to the Gaussian mechanism, this one is epsilon delta differentially private. And notice that we in this algorithm, each party, they just need this one step. So there's no sharing or communications between parties for now. Then we are going to check how's the ordinary least square solution on this release data. We denote X DGM as the selected features in release dataset and labels Y DGM in the release dataset. And the right here, this is the optimal solution. We will compare these two solutions then. First compare these two terms. First we can decompose X DGM and Y DGM into the private feature matrices and private label vectors with the additional Gaussian noise Rx and Ry on top of them. This is followed by the follows the definition of the release algorithm. And then we further decompose them into these 4 parts. So the last 3 terms, so by assumption, we know that x, y are bounded by 1, and Rx, Ry are Gaussian matrices. Their variance is not related to the n. Then the concentration theorem, such as Hofstadter inequality, implies that each entry in this in those matrices will converge to 0 in probability. And then union bound helps us to prove that this whole vectors and the summation of them will converge to 0 as well. And the first term, again, because x and y are bounded, they will converge to the expectation as well. And this is what we need, which is great. But then we take a look to the comparison between these 2 inverse terms, or the matrix inside the inverse term. Again, we decompose the XDGM to the X, the feature matrix in the private data set, the original data, and Rx. So similar to the previous derivation, the X is bounded, and Rx is a Gaussian matrix not related to the n. And the concentration theorem implies that these 2 terms converge to 0. However, now the last term, Rx transpose Rx, this term will converge to this diagonal matrices with the diagonal value, that is the variance of the Gaussian random variable of Rx. So this bias is very bad. So it's bad because such bias would not diminish as the data set goes to infinity, which means that even if you have infinity data, that is the ideal case for the differential privacy. You won't, this bias won't be overcome. And moreover, someone may say we can treat it as an as the regularization for the ordinary square solutions. However, this bias is indeed very large. So when epsilon is 1.0 and delta is 10 to the minus 5, then the variance, the sigma epsilon delta is mostly 4.8. But we know under our assumption, the first useful term here, each value is bounded by 1. The absolute value is bounded by 1. So this bias will dominate the useful matrix that we want to keep, and we will expect that it will destroy the performance. So one easy revision is to subtract such bias. Right? We can subtract for the max sigma square I from the original estimate of Hessian terms. And with this debiased operation, we have the correct convergence. However, there's still one concern, which is the small eigenvalue issue. Now this matrix is not guaranteed to be positive definite anymore. Then the support of this eigenvalue, so X here, XDGM is a random matrices, right? The support of eigenvalues include 0, then which makes the eigenvalue more likely to be very small. And this possible small eigenvalue will lead to explosive matrices after the inverse operation. So directly applying Gaussian mechanism looks very hard to work very well, and because of that bias that can be overcome by. And so we ask, can we design an algorithm such that the bias would diminish as n goes to infinity? Okay, then I'm going to introduce our main algorithm. So first, we share a random Bernoulli matrices, 1 minus 1 Bernoulli matrices B to all parties. 1 minus 1, they are they have the probability half and half. So here is an example of random matrix B. It's 2 by 3. And for the K, so the N is the size of private data, and K is a hyperparameter that we want to choose for this algorithm, and we will decide it later. Then we then go through the privatization algorithm at party J. So the first step is mixing n data points into k data points by the Bernoulli matrix B. So how to mix these n data points? We can see an example. So to mix the first data point, we select the first row of this random matrix, and we multiply those 1 minus 1 value to the data point, corresponding data point in the private data matrix, and sum them up to get our first mixed data point. And this is the how the second one is mixed. Again, it's a summation of data point times 1 minus 1. But right now we take the second row of the random matrix B. We can write it in a matrix format. It is equivalent that we multiply this random matrix B before the private data matrix DJ. We further multiply this factor 1 over square root k as a normalization. Then we apply the Gaussian mechanism. We add the Gaussian matrix Rj to make it epsilon delta dp. And by carefully computing the sensitivity of the first step, B is also taken into account. We compute that the sensitivity is again the 2 square root of Dmax. So the variance here is designed as 4 Dmax and sigma square. So after adding the Gaussian matrix Rj, the values are more noisy. There are two comments here for this privatization algorithm. The step A, this mixing step is very crucial. We'll see that such design keeps the data property in some metric, which is useful for the linear regression performance. And secondly, such mixing helps hide each single data from the output. Then intuitively, less noise is injected to guarantee the differential privacy. And we'll see how it helps in the later derivation. Okay. To simplify the privatization algorithm at party J, it's to multiply project n data points to the k data points by this matrix, and then add the Gaussian noise. That's all it is. And then finally, all parties jointly release this concatenated matrix. Okay, so this is what the algorithm looks like before moving to the analysis. Any questions so far? Okay, cool.
You didn't show us how the sensitivity changes, did you? You're so far still assuming RJ is 4D max sigma squared epsilon delta.
Yeah, so sorry, I didn't make slides for it, but I can explicitly, I can briefly explain it. So the easy case is that we assume, if we assume k is just 1, so we only want to mix all of them into one data. Then, yeah, let me go to the previous slides. Okay. Then, so if we will only have one data point here. It's a mixing of all single data in the private data matrices, multiplying the 1 and -1. Then consider another neighboring data set to contribute this mixed data point. The difference would be only one of them, right, in this summation. So if it is the first one, then the difference would be the -1 multiply the difference between the two different data points. So such difference is 2 times square root of dj, like the 2 here. So this is the sensitivity for if k is set as 1. So if we have k data points, so that's why we have this normalization here. So for one data point, the sensitivity is 2 times square root of dj. So for k, it becomes 2 times square root k dj. So we have with this factor, then the sensitivity is square root 2 dj. Okay, does it answer your questions?
Yeah, thank you.
Okay. Okay. Yeah, so this is our release algorithm, and then we are going to check the linear regression solution on top of it. So again, the left is the ordinary least square solution on released data, and the right is the optimal solutions. Again, we first decompose the this public feature matrix into the additive Gaussian noise matrix and the projected private data matrix, and write them into this three-part. So the analysis for the first part needs the introduction to the JL lemma. Okay, so this is the informal definition for the Johnson and Lindenstrauss lemma. So it is after the random projection by 1 - 1 Bernoulli matrix B. So here we map a set of vectors from V1 to 1 over square root K B times V1, and same for the remaining vectors. The inner products are kept between these vectors. The kept is that for any pair of I and J, the inner product between Vi and Vj is mostly wouldn't be different a lot from the projected vectors. And the probability that such difference is smaller than error beta for all pairs of I and J has the probability 1 minus these exponential terms. So this exponential terms is exponential to the K, the dimensionality that you will project from the original space. So here, if we think of the set of vectors in the JL lemma, we think of them as the column vectors of X. Then we can, by applying the JL lemma, it will be approximate to just X transpose X. Because each entry in this X transpose X, it's just an inner product between the column vectors of X. And moreover, we need this K be omega 1 to make this convergence improbability hold. So omega 1 here means that K is a function of n, and K will go to infinity when n goes to infinity. And for the second part, I omit the details here, but so the idea is simple because X is bounded, and Rx is a Gaussian matrix. We can first prove that the multiplication between this projection matrix and Rx is also approximate to a Gaussian matrix. And then by some concentration theorem, we can show that this second part will converge to 0. And now this third term, which is very similar to the previous bias term, this is interesting because now we know that after our mixing, we only have data points, K data points. So Rx is it's K by D. Then the scaling of Rx transpose Rx should be something related to K. And so then if K is smaller than this n, the order n, then this term will converge to 0. In details, we can have the new factor 1 over K for the Rx transpose Rx, and then the inside term will converge to these diagonal matrices with the value of the variance of those Gaussian random variables. And the first term k to n, if k if we set k as small n, then such convergence will hold. Okay, so we checked these three terms individually from the second equation, second line to the third line, and we can now see how the mixing step helps for this equivalence. So first, such mixing step keeps the inner product between the column vectors of x and y. So that's how the first term in the second line and third line could be equivalent under the convergence improbability. And second, the bias term from consisting of additive Gaussian noise is only, sorry, it shouldn't be k by k. It's only related to order k, and we can choose small k to guarantee that the last term would converge to 0. Okay, and then this term will further converge to this expectation by the concentration theorem again, because values in X are bounded. So so far we showed that if we carefully select K, such that K is not very small and it's not very large, some midpoint like square root n, then this convergence will hold. And similarly, we can show that the x transpose y terms, the convergence also hold, and then together we can show that the learned weight will converge to the optimal solution when n goes to infinity. So this is the main theorem of our paper. So it shows how to select k. So if we choose k in this order, so this order for n is square root n, then the probability that the difference between the learned model and the optimal weight larger than any beta is smaller than an exponential terms, and this and square root n is inside this exponential stuffs. Okay, that's all for the method. Do you have any questions, or I will move to the experiment? Thanks. Okay, let's quickly go through the settings of the experiment. So this is the experiment on synthetic data set. This is how we construct the data. First, we assume we have 6 parties in total. 5 of them have 2 attributes, and 1 of them only has 1 single attribute. For the party that has 2 attributes, the attribute values are ID sampled from a uniform distribution, -1, 1. So they are all independent. And for the party that has single attribute, which would be the label for our linear regression task, we generate it by computing the inner product between W and the feature vector. So W is ground truth in your model, and we sampled it once from this uniform distribution and fixed them when we conducting the experiment. So this range would guarantee that the DI6, this value would also be bounded by 1. Then the learning task is to predict that single attribute from all remaining 10 attributes. We will vary different sizes of data set, and I will show the result for this privacy parameter setting, epsilon equals to 1 and delta equals to 10.-5. And in our paper, we do more epsilon values. And then this is the method that we measure for this experiment. The first is OLS directly on private data. It is treated as an upper bound for this result after the privatization algorithm. And the second is the ordinary least square solution on release data when we directly applying Gaussian mechanism to the releasing algorithm. So we denote it as BGM OLS. So B here names bias because the term inside this inverse is has the bias. And the second is and the third DGM OLS is that we debias the term from above. And the last one is our proposed method, random mixing strategy before applying the Gaussian mechanism. And for the evaluation, for the learned model W hat n, we will measure the probability that the difference between it and the optimal solution larger than beta. So this probability is measured by repeating. So because we already claim that this probability, the randomness of this probability comes from the data sampling and randomized algorithm. So we measure this probability by repeating the data sampling and the randomized algorithm. And we want to check if this probability converges to 0 when n becomes very large. So here is the result. Different lines are different methods. And these 3 figures are measured for the 3 different beta values. So beta is the error, the lower bound of the error that we want to measure. So we can see that first, for the OLS, it's always very good, close to 0. And for our new proposed method, RMGM, it converges to 0 when n is large enough, large as 3 millions. However, for the DGM and BGM, they never converge to 0. So this is one more page to support the small eigenvalue issue of DGM OS that we mentioned before. So in the DGM, because we subtract the bias from that Hessian matrix, then that matrix is not guaranteed to be positive definite anymore. Then we claim that the eigenvalues of that matrix before the inverse could be very small. And this is the result to support that claim. So these blue points are the absolute eigenvalues, the absolute values of eigenvalues. And the red one is the eigenvalues of our method. that matrix before the inverse. So we can see that the DGM-OLS, it has way more small eigenvalues than our proposed method. And accordingly, the difference, because is much higher than our method. Yeah. So in conclusion, first we define our problem setting of data release for vertical distributed data, and then we show that directly natively applying Gaussian mechanism won't work very well. And then we apply a mixing strategy before the Gaussian mechanism. Then with any selected features and label from released attributes, the OLS solution is guaranteed to asymptotically converge to the optimal solution on the private data distribution. And last, our experiment on synthetic data show the effectiveness of our proposed method. Yeah. So here are the references, and thanks for the listening.
Thanks for the presentation.